This lesson is for Chapter 2, Section 4, A Library of Parent Functions. If all of you guys would please get your notebooks out and start in your textbook on page 198, we will get this started. A linear function, this is going to probably be one of the ones that you're most familiar with, is going to be a graph of a straight line. If we were doing a problem such as this, which you will see in your homework section, write a linear function f for f of 2 equals 6 and f of 4 equals negative 9. We're looking for a linear function, or a y equals mx plus b equation, utilizing these particular values. Now, if you're remembering f of x notation, the number inside the parenthesis is an x value, and the solution for an f of x is a y value. So both of these pieces in here represent a point. So the first point that I see here is negative 2, 6. And the second point with the f of 4 equals negative 9 would be 4, negative 9. Now we've already worked with writing linear functions given 2 points. So let's go ahead and find our slope if these two points lie on our function. We'll have negative 9 minus 6 all over 4 minus a minus 2, or negative 15 over 6, which is negative 5 halves. Now, using my point slope form, if I use one of my points for my x and my y, and I'm going to choose the first one, I would have y minus 6 is equal to negative 5 halves times x minus a minus 2, or x plus 2. So simplifying, I'll have y minus 6 equals negative 5 half x minus 5. Add 6 to both sides. So my function, if I were to write it in function notation, would be this. And I'd be satisfied with either y equals negative 5 halves x plus 1, or f of x equals negative 5 halves x plus 1. Alright, so those we've worked with before. That shouldn't be so bad. Quadratic functions are going to give us a graph that looks like a parabola. Alright, so those are our x squared. Y is equal to something x squared plus something x plus a number. We've worked with those. Cubic functions, of course, are going to have a cubic variable in them. Those are going to be symmetrical about the origin and will kind of look like the curve that I put on the slide here with this statement. The next kind of parent function that we're going to be looking at is a graph of a square root function. This one I was entirely unsuccessful in typing, so I'm just going to draw it here for you. It sort of starts at the origin and curves in the positive direction off into infinity. Okay, remember that square roots, in order for them to have real solutions, have to be positive. So that's why this one goes off in that direction. The graph of a reciprocal function. Reciprocal function would be something like f of x is equal to 1 over x. Okay, so keeping that reciprocal thought in mind. The reciprocal function is going to be also symmetric with respect to the origin. It looks like identical curves that never quite reach an axis. So something that would be kind of like this, but they never quite get to those axes marks. And of course, if it's symmetrical, it's going to have a buddy on the other side as well, just like it. Greatest integer function. These are probably going to be the ones that you are the least familiar with, so make sure you're looking with me on page 201 right now. This notation is probably also going to be new. A greatest integer function will have a graph that appears like steps. The notation of, well, it's kind of a double bracket with a function in the inside means the greatest integer less than or equal to x. Okay, so remember, an integer cannot involve a decimal or a fraction. Okay, so when we get a value for our function, If that value is an integer, that will be our answer. If that value ends up being a fraction or a decimal, you're going to drop down to the next closest integer value. Okay? So that double bracket notation means the greatest integer less than or equal to x. The graph that they gave us on the page 201 there kind of looks like steps in this respect. Had a step and open dot. That was supposed to be open. Fill dot to open dot, and so on and so on and so on. You can see it in the book there a whole lot better than I can draw it. All of these parent functions are summed up for you on page 202. So if you turn to page 202 right now, all 8 of them are located on that page. One that actually I didn't mention yet that wasn't outlined for us in the section here is the absolute value function. Okay, that absolute value function is the third one on the top row there, and they end up looking like a V. Okay, so absolute values look like that. The rest of them I think we caught. Now let's take a look at another checkpoint problem. Turn back to page 201. At the bottom there, we're going to evaluate one of those piecewise or step functions just because they're probably the least familiar to us. That particular one said evaluate the function when x is equal to -3 halves, 1, and -5 halves for the function f of x equals x plus 2 with that double bracket notation, that integer less than or equal to x. Alright, so let's tackle this. Let's set up f of -3 halves. So that means substitute in -3 halves for x into your function. And if we evaluate that, we're going to get 1/2. Now, what would be the greatest integer less than or equal to x? Well, 1/2 isn't quite 1, so we can't go there. The integer just below that would be 0. Okay, let's move on and do f of 1. So now substitute 1 in. And we're going to get integer greater than or equal, or less than or equal to 3, excuse me, and that would be 3. Last one, f of -5 halves. And if we evaluate -5 halves plus 2, we get -1/2. The integer less than or equal to -1/2 is going to be -1. So there's the 3 values that we would get for that function. Now, checkpoint problem number 3, look to page 202 again. We're going to sketch the graph of f of x. And this is another one of those piecewise ones. For any x values that are -4 or under, we're going to use the function -1/2 x minus 6. If we are looking for a value that, or looking at a value that's bigger than -4, then we're going to use the bottom function x plus 5. So let's just plug a few values in here. Let's do f of, let's go -10. Okay, so that'll be the top function. -1/2 times -10 minus 6. -1/2 times 10 is 5. 5 minus 6 is -1. So one point that we could graph is -10, -1. Let's choose another one in that range yet. Let's go like with f of -6. So we're going to have -1/2 times -6 minus 6, or +3 minus 6, which is -3. So -6, -3. Let's do another one. Let's do -4 itself. Since that top function is for less than or equal to negative 4, we are still using that top function. So negative 1/2 times negative 4 is 2, minus 6 equals negative 4. So that looks like we're going to have a straight line from negative 10 to 4. And those are going to be closed dots along there because the negative 4 was included in the x values. Now when we move on into some values that are greater than negative 4, we might have to take that into consideration. Let's pick f of negative 3. Okay, so now we're on to that other function. Negative 3 plus 5 is 2. So negative 3, 2 is a point. If we were going to put negative 4 into that equation, or into that function, we would be at 1. So I'm going to put an open dot at negative 4, 1, because there will be points just to the right of there, but it just won't include negative 4 itself. Okay, now when you look at this function, it does have a slope of 1, so we know that this is going to keep increasing. And we can finish our graph. Okay, you guys have a shorter assignment this time. It's just pages 203 to 204. Grab a couple from each section again, see what you think. Come back to class with some ones that you can't quite figure out or you'd like to look at together as a group. All right, see you later.